All right, let's dive right into this. Imagine waking up one morning to find out that a massive, critical chunk of the internet just lost power. And I'm not talking about a quick server glitch at some tech headquarters in Silicon Valley or a localized outage in New York City. I'm talking about an unprecedented electrical shock that struck on July 22nd, 2026, in a region most of us wouldn't even associate with the digital world. Welcome to our explainer on exactly what happened the day the AI capital of the world went dark and what it reveals about the hidden physical foundations of our modern lives. So, on that seemingly normal July day, a major high-voltage transmission line unexpectedly went offline. And within moments, a staggering 3 gigawatts of electricity demand disappeared almost instantly from the PJM interconnection, which is America's largest electric grid. To put that massive number into perspective, imagine several large power stations suddenly realizing that their customers had just vanished into thin air. Grid engineers had to absolutely scramble to stabilize the system as voltage fluctuations rippled across the entire network. But what exactly had suddenly disconnected from the grid with such a massive appetite for power? Well, to answer that, we have to look at the massive contrast between what we think the internet is and what it actually is. We've all been trained to imagine the internet as this invisible cloud, right? A wireless magic trick connecting our phones and laptops. But the physical reality is incredibly heavy and industrial. Every email, every video stream, every single AI prompt travels through millions of miles of cables, fiber optic networks, and massive facilities that require staggering amounts of constant electricity. The internet isn't magic. It is very, very physical. And get this, the physical home of the internet isn't in California. It's actually in Northern Virginia. If you drive through certain counties out there, you'll see dozens of these ordinary-looking, windowless warehouses with no storefronts and no flashy signs. But behind those heavily secured walls lies literally the greatest concentration of computing power ever built by humanity. This region quietly became the digital capital of the modern world, processing everything from government systems and online banking all the way to the complex AI algorithms we use every single day. Now, Northern Virginia didn't just pop up overnight. Back in the 60s and 70s, it started out as a strategic hub for telecom and defense tech, mostly due to its proximity to Washington, D.C. Then in the 90s, the region became a critical junction for the massive expansion of fiber optic networks. After that came the 2000s, where the cloud computing boom led tech giants to rent out server space rather than build their own, which drove explosive growth in the area. And today, we are squarely in the AI infrastructure revolution, which is demanding more power and space than anyone ever anticipated. So the crucial question is, why did all these competing companies decide to set up shop right next to each other? It comes down to something called an internet exchange point. Simply put, this is a physical location where internet networks intersect to exchange data. Once the first major exchange points were built in Northern Virginia, this unstoppable network effect took hold. Companies didn't just move there for convenience, they moved there because everyone else was already there. The more networks that connected, the more valuable the location became, effectively forcing every major tech player to build their data centers in this exact same region. Section 1. The AI Catalyst. Okay, there is an immense difference in the energy required depending on what you're actually doing online. A traditional internet search is relatively passive. It's mostly about retrieving existing information from a database, which requires minimal processing power. But an AI prompt? That is an entirely different beast. An AI assistant doesn't just fetch information. It performs billions of active mathematical calculations in fractions of a second to predict words, analyze context, or generate images. It is exponentially more energy intensive. And inside these facilities, that massive energy consumption is split into 2 main categories. The first slice is the power needed to actually run thousands of GPUs and specialized processors simultaneously, 24 hours a day, for weeks or even months at a time. But doing billions of calculations generates a tremendous amount of heat. So the second slice, the continuous industrial-grade cooling systems required to prevent the equipment from literally melting down, well, that consumes nearly as much energy as the computers themselves. Because of these staggering demands, we've completely moved past normal server rooms into the era of the hyperscale data center. These are massive, massive facilities that operate 24 hours a day and can consume as much electricity as a small city. They function less like traditional tech offices and a lot more like 24/7 industrial factories. But instead of producing steel or cars, they are manufacturing computing power and intelligence on an absolutely unprecedented scale. Section 2. The vulnerability and the fix. So what happens when a region this power-hungry loses its connection? Well, a highly engineered, automated emergency survival protocol is what saved the internet from collapsing that day in July. When that high voltage line failed, this system kicked in flawlessly. Step 1, the facilities instantly detected the abnormal power conditions on the wider grid. Step 2, rather than wait for the disturbance to fry their systems, the data centers automatically disconnected themselves from the regional grid. Step 3, massive battery rooms provided instant, gapless emergency power for a few crucial moments. And finally, Step 4, roaring diesel generators fired up to supply ongoing electricity. All of this happened in mere seconds. The real reason millions of people streaming videos, banking online, and using cloud services didn't even notice the outage is summed up perfectly by this quote from our source material. Reliability is not accidental, it is engineered. Those backup generators, battery rooms, and redundant fiber connections represent billions of dollars of proactive investment. The system worked exactly as designed, but it also proved that our entire digital economy is completely dependent on physical resilience that costs a fortune to maintain.
Section 3. The infrastructure race. To keep up with AI, the global demands right now are just staggering. It is no longer just about writing smarter software. Nations and companies are racing to secure massive new electricity sources, from upgrading grids to exploring new nuclear technologies. They have to build incredibly advanced, multi-billion-dollar semiconductor factories just to make the chips. They're expanding fiber optic networks across oceans and aggressively developing new ultra-efficient cooling technologies. It's really an industrial boom masquerading as a software update. And because having all your digital eggs in one Northern Virginia basket poses massive concentration risks like natural disasters or localized power failures, the future absolutely has to be distributed. The huge lesson from the 2026 grid shock is that expansion can't just happen in one zip code. To reduce vulnerability, companies are actively spreading their next-generation AI infrastructure across North America, Europe, Asia, and the Middle East, fundamentally rewiring the physical geography of the internet.
Section 4. The backbone of civilization.
What is absolutely crucial to take away from this explainer is that the true bottleneck to our future isn't just silicon chips, it's human talent. Building this hidden backbone requires electrical engineers, network architects, specialized construction workers, cybersecurity experts, semiconductor designers, and power grid operators. The AI revolution isn't just happening on a computer screen, it is being built beneath our feet by a massive array of engineering and blue-collar talent. They are the ones actually keeping the modern world online. Which leaves us with this final, incredibly important question. Can the world's physical infrastructure and energy systems actually grow fast enough to support the next generation of human innovation? The next time you casually ask an AI assistant a question or seamlessly stream a movie, remember the invisible, power-hungry factories humming 24/7 to make that moment possible. Our digital future isn't just about writing better code. It's about whether we can engineer the physical strength to sustain it. Thanks for joining me on this explainer, and I really hope it completely changes how you look at the cloud.